Hello! Good day! We are Project Optical. Optical stands for Optical Payload Technology In-Depth Knowledge, Acquisition, and Localization. We are a project under the Stamina for Space program of DOST PSHERD. Our implementing agency is the National Institute of Physics under the leadership of Dr. Maricor N. Soriano. For our virtual open house today, we will be showing you the exciting equipment we use in our research, specifically our line scan camera testing platforms. But before anything else, let us first talk about the project's objectives, one of which is to develop optical payloads for aircraft or satellite platforms. These are intended primarily for agricultural monitoring and disaster assessment. So, how exactly can a camera in a drone help monitor vegetation? Each vegetation has a signature which suggests their health and condition. To get these signatures without using a camera, we would be needing to gather each data point by point during a fieldwork using a spectrometer as shown in the picture. These will be tedious and time-consuming. However, with the help of an airborne hyperspectral camera, we can get all these signature data in a single shot. That means we can potentially recover multiple signatures, thus monitor the health of a massive area of vegetation with much less time. Much more data in much lesser time potentially yield better and more efficient analysis. Project Optical is divided into three multidisciplinary teams. The airborne team designs and calibrates an imaging system for an aircraft like a drone or a plane. The mechanics and flight team designs and develops mechanical systems for the imaging systems of the airborne and spaceborne teams. And the spaceborne team creates the design and draws qualification of an imaging system for a satellite. Currently, we are designing and developing two optical payloads. Both are push broom cameras. The one on the left of your screen is High-P. High-P is an airborne hyperspectral push broom camera. The other one on the right is Malikmata. Malikmata is a spaceborne Rgb push broom camera. You might be wondering by now what a push broom camera is. Unlike a typical camera that takes a full 2D image in a single shot, push broom camera has a scanning imager that constructs an image by stacking series of line images, which corresponds to a series of multiple shots. We have mentioned earlier that one camera is an Rgb camera while the other is a hyperspectral camera. Now, it's time to characterize each. Most of the cameras commercially available are Rgb cameras. An Rgb camera captures three separate images of the scene, each for the red, green, and blue spectrum information of the area. Combining these three images results to what we perceive as a colored image. This colored image is comparable to what we can now observe through our naked eye. Meanwhile, a hyperspectral camera captures much more spectral information by getting an image for a desired wavelength. By getting this much information, we can better recover the signatures of our target objects to better analyze their condition. In any scientific development, testing is a vital part. Now, we will show you the different testing platforms in the optical laboratory which we use in approximating the scanning motion needed for a push broom camera. First on the list is a motorized rail called Niji. Niji is originally designed for scanning artworks, but our team has been able to adapt this rail to help in our study. Our payload is mounted on Niji looking directly downward to the target object, which is illuminated with an array of white LEDs. With a specified platform speed, frame capture interval, and exposure time, Niji moves scanning through the target, which lets High-P capture a line in space with its corresponding wavelength components. The captured frames are then stitched together. The test images used are a series of line pair patterns and a Macbeth color chart for analyzing spatial contrast and the spectral response of the hyperspectral imager. The results show little to no imperfections in the stitched image, showing the ideal scanning motion approximated by the Rgb motorized scanner. Next on our list is a motion-free way of testing our cameras. During the early stages of our development, some parts of the camera were still not present. Unfortunately, the digitizer, which converts analog signals into digital data, and the camera lens, which focuses the light onto the camera sensor, were not yet in the team's possession at that time. This made it harder to test using the previous platform, Rgb. To be able to test our camera sensor prototype, we then created a testing setup that doesn't require any mechanical parts. This projects an image on the sensor and allows us to obtain the digital image data to process and analyze. The setup only requires your typical projector paired with a single focusing lens. This is how the setup works. The projector will scroll the target image on the camera sensor, and the sensor's output will be captured line by line until we complete the entire image. Shown here is the actual experiment setup in the lab. The photo on the left is a projector with a single focusing lens. On the right, you can see a line camera sensor connected to an oscilloscope along with the projected image. Light on the sensor will be converted to electrical signals. Then, the oscilloscope will convert the electrical signals into digital numbers. The data will then be rendered to recreate the image in a computer. Here we have the result of the experiment. Only 50 lines were captured to render this image, which explains its pixelated appearance. Still, we are able to prove that the camera sensor prototype works. Last on our list of testing platforms, the rotating mirror jig. We developed and fabricated a rotating mirror device as an alternative scanning mechanism for imaging systems. This simplifies testing for scanning payload prototypes. The device is portable and can adapt to a wide variety of camera setups, light sources, or target objects. The main purpose of the device is to simulate the motion of drone or satellite platforms for the early stages of optical payload prototyping. The main parts are the mirror, which rotates about a shaft, the stepper motor and its driver, the gearbox that controls the speed of the mirror rotation, and the microcontroller that controls the stepper motor. Shown here are some footages of the rotating mirror jig in action. The reconstructed image at the bottom shows a panoramic image of a scene that is gradually completed as the mirror rotates. The video at the upper middle part is the camera's live feed, and each frame of that video is compiled to create the panoramic image. We consider the laboratory testing platforms of our projects as testaments to the creativity and skills of our Filipino scientific researchers in order to adapt to the situation while delivering the objective. I hope you enjoyed learning about our project's laboratory testing platforms. On behalf of the researchers behind Project Optical, we thank you for your time. If you want to know more about Project Optical, you can email our project leader, Dr. Maricor Soriano, at msoriano@nip.upd.edu.ph. Be safe and healthy!